Hello everyone, in this lecture we are going to learn about Annex F of API 650. Our flagship courses are Master Static Equipment Design and PVElite, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs. So do visit our learning platform for more details on scootoid.thinkific.com.
Annexure F is for small internal pressure. Okay. Now, what do you mean by small internal pressure? See, these API 650 are already there with a small internal pressure. Right? So what do you mean by small internal pressure? 18 kPa, the limit which you see here. That is there for the normal tanks also. Right? So what do you mean by design of tanks for small internal pressure? Okay. So for that, let me give you one flow chart, okay, which is part of the Annexure F itself, which is very important. It's called the decision tree. How you will decide whether the tank will be designed by using Annexure F or not. The use of Annexure F is required or not. Okay. So the calculation will start with this. Okay. Ready to see that flow chart? Okay. So let us see the decision tree. Okay. First question you'll be asking, does the tank have any internal pressure? Like any internal, like in our case, was there any internal pressure? The tank we designed, whether it was having any internal pressure? The answer is no. So what will be following? The basic design. What we did, okay, by using the general design. We didn't use Annexure F. But now there is a small pressure which is there. Then what? We'll be checking this step now. Okay, if small pressure is there, then does this internal pressure exceeds the weight of the roof and whatever is attached to the roof? That means what you are checking basically. If this is my roof, this is my tank. Okay. So first I'm checking that if the joint between shell and roof is weak, okay, which we keep for the frangible type of roof. Okay. Now let us put some highlight here on the frangible roof. Roof joint will fail prior to the bottom. So when we say frangible roof design, that means what we are saying is that this joint, which is between shell and the roof, that will be weak compared to the joint between shell and the bottom plate. Okay. And when the pressure is high and if something has to break, see, normal condition will not like it to break, right? But if in the case of any fire, okay, or suddenly pressure rising and there is for some reason whatever vent you have provided that is blocked, you're not able to vent it, or the vent capacity is not sufficient. Okay. In that case, the tank will, if having pressure, it will try to blow. Okay. So if it is blowing, it should blow from here, not from here. What is the advantage? In any case, it is breaking. So what is the advantage? Does it matter if blows from here or blows from here? Does it matter if the roof is failing or the bottom plate is failing? Yeah. Bottom joint failure will throw tank like rocket. Okay. So even the roof failure will throw the roof with a high speed because the weight is less. Minimizing product leak. Okay, that is basically the concept. Okay, no leak of the whatever liquid you are having. Okay, so you are storing some liquid. That liquid itself may be dangerous. Okay, when it is going outside, if it catches fire, whole plant will be on fire. So you don't want that. Okay. So if something goes wrong, some pressure is becoming higher, if the roof is only failing, suddenly the pressure will be dropped. Okay, pressure will be dropped and you can control, you'll have time to control the things. Does it make sense, guys? So now for that case, okay, so if roof is failing, when the roof will, consider this case, if the internal pressure does not exceed the weight of the roof, in that case, what happens? Whether it will be able to stress out your joint. Say this is my roof. Okay, this is my shell. There is an internal pressure. So internal pressure is basically what it is trying to do, creating a force in the upward direction. Weight is downward, okay? And weight is more than the pressure. So why it will experience any load in this? No, right? The weight will counter that. Okay. So in that case, again, even though small internal pressure is there, but the pressure is not exceeding the weight of the roof. Okay. Now, how you'll be doing this calculation? Just multiply pressure into the area of the roof. That will give you the force and convert the weight of the roof into Newton by multiplying with G. You can compare, right? Make sense, guys? How you'll do the checking? Yes. So got it. So if it is not, internal pressure is not exceeding the weight of the roof, in that case, again, basic design you can do. There is no additional calculation required. But now, what if the answer is yes? Internal pressure is exceeding the weight of the roof. In that case, you'll be moving to the next step. Now you'll be checking what? Does internal pressure exceeds the weight of the shell, roof, and the attached structure? Now you'll be checking, okay, so whether if it is more than roof, but is it now more than the roof plus shell also? And definitely when we are saying shell, we are considering whatever is attached to the shell. Okay, if there is some structural arrangement which is supporting the roof, that will be definitely either part of the roof or it will be part of the shell. So that also will be included. If there are stairs, that also will be included, or railings, nozzles, everything will be included in that. So now you'll be checking, does the internal pressure exceed the weight of all the tank? What we are leaving is only the bottom plate. Okay? Because now what we are considering that it will fail from here, okay, and it will go upward, okay, by failing at the bottom part. Make sense? If it is not, okay, if the internal pressure is not exceeding the weight of the cell and the attachment, then you have to do Annexure F1, but there's a different rule. Like you'll be following from F1 to F6. We'll see that. Okay. And you'll be calculating some P max. Some calculation will be there from Annexure F. Okay. If the answer is yes, if it is exceeding even the weight of the shell and the attachment plus roof, in that case, you'll be checking whether the internal pressure exceeds 18 kPa, because that is the limit of API 650. So if your answer is yes for this also, then it is saying go to 620. Okay, you are in the wrong code. Okay. If the answer is no, then there will be additional calculation. Annexure 650, which is like F7 and F8. We will see that what additional calculation will be done. So that will be required. Is that making sense, guys? So you have three different scenarios. One is if there is an internal pressure, but the pressure is lesser than the weight of the roof. In that case, basic design is sufficient. Okay? So you won't be doing anything additional. Now, if the pressure is exceeding your weight of the roof plus the weight of the shell also, in that case, there will be some additional calculation as per Annexure F, which will be required. Now, if it is even exceeding the roof, but less than the 18 kPa. Okay. If it is exceeding that, okay, then you'll be only doing some additional steps. Few more additional steps based on API will be required. Annexure F will be required. Okay. So if your internal pressure P is such that it is more than the pressure because of the roof. Okay, I can convert that into pressure, or I can consider as a weight. So, or force. Force because of pressure. If it is more than the, if the force because of pressure is more than the force because of the weight of the roof, then what? If the internal pressure exceeds the weight of the roof, what you'll be doing? Internal pressure exceeding weight of the roof. What, any additional calculation will be required, or general design is okay? Basic design is okay. You'll be performing basic design, or Annexure F also will be there. If your force due to pressure is more than the F1 to F6. Yeah, so I'll definitely, it's less than 18 kPa. Okay, pressure is less than 18 kPa, but the pressure is more than, and it's also less than the shell and the roof. Okay, it's lesser than this, but more than the weight of the roof. Then Annexure F1 to F6 is what you'll be doing. If the pressure is more than weight of the roof plus shell also, in that case, 2 additional steps will be added. Okay, we'll see that. And last, if it is more than 18 kPa, then Annexure API 620, API 620, not Annexure. Make sense? Okay, first it will start with this. Okay. That shell thickness. In calculating shell thickness for Annexure F tanks, okay, and also selecting manholes, everything, you'll be using the general design formula. What change will be there? Any change if there is a design internal pressure? If there is an internal design pressure, will there be any change in the formula which we have used? What additional thing you'll be doing? We have already seen that. Converting that pressure into static head, H. Okay, we have already seen that getting added. So if there is an internal pressure, add that in the total height and do the calculation by using same general design principle, basic design. Okay. And even for the selection of the nozzles, thickness and all, we'll be doing that. Now, okay, apart from that, you'll be also calculating a maximum design pressure, okay, which can be exerted on the tank. Okay, so that you can check whether your design pressure is not more than that. Okay, so maximum design pressure that tank has been constructed, okay, for the basic design, whatever you have done. Okay, so this calculation you'll be doing, that will give you the maximum pressure which you can apply. This calculation you'll be doing, and then you'll be making sure that whatever maximum pressure which you have calculated, that is less than 0.8 times of PF. What is PF? PF is again one pressure which you'll be calculating, which is called failure pressure. Okay, so you'll be calculating the failure pressure for the tank, a pressure at which the tank will fail. Okay, maximum pressure which can be applied. Okay, and then you'll make sure that your pressure which you are applying, P max, is at least less than 80% of that. Okay. So maximum pressure which you can apply should be less than 80% of the failure pressure. Make sense? So this will allow that you have a safe margin between whatever pressure you have considered. Got it? So you'll be calculating the maximum pressure, and this maximum pressure, if you see, it depends upon the A. Okay. Other factors are definitely like weight and the diameter, theta. One parameter is A. A is what? It's a participating area between roof to shell joint. Okay. So your all calculation depends upon that. What is the participating area? Okay. So how participating area is calculated? For that, you can see this figure. Okay. So like if your tank construction is like this, then first you'll be calculating the WH. So WH multiplied with TH will give you the area in the roof. Now the question will be how I'll get WH. What is WH? So for that, you'll see here. WH is maximum width of the participating roof calculated by this 0.3 times under root R2TH or 300. Okay, R2 and other parameters are already defined here. So you can find that. So whatever is the less, okay, that will give you WH. So multiply the thickness, you'll be able to get the participating area in the roof. Then you'll be calculating LE. What is LE now? Again, see here. It is. Okay. LE shall be limited to 250T under root Fy. Okay, that is the value of LE. Okay. So LE also have calculated. So I can calculate the thickness is known because whatever angle I'm selecting, that is there. The next thing will be WC. This is again one unknown. So WC, how I'll be calculating? I'm using this equation. This is the maximum width of participating shell. So this is just the area calculation. Okay. So you'll be calculating the participating area, and then you'll be comparing that with this. Okay. So whatever area you are calculating as a participating area, that should be more than this area. Getting it? So you calculated area based on the different area values given, whatever construction is there of your tank. Then whatever value I'm getting, let us say I'm getting 2540 mm square. That should be more than whatever value I'm getting here. Is it making sense? Great. Okay. So area required for compression and area which is participating. Yeah, same area which I have calculated based on the participating. I'll be using this for the maximum pressure taking capability calculation. So what is the maximum pressure my tank can take? Okay. So all these calculations you have to do when your pressure is exceeding the weight of the roof. Roof plate design, now it's a cone. Okay. Cone is getting designed for an internal pressure. So you can see that this equation is nothing but calculation of the thickness. Okay. PD or PR divided by 2T. PR divided by T. Okay. Because it's PD by 2T. So PR divided by T. So using that for calculating the thickness of the roof. Okay. Divided by cos alpha because it's a cone. Making sense? This additional calculation you have to do for the thickness of the cone. Is it making sense? These calculations are when you have a small pressure which is exceeding the weight of the roof. So Just learning the process is what you need right now. Now, if you have a dome or umbrella roof, then also you have a thickness calculation formula. So 0.5 for the dome roof, 1 for the umbrella roof. So use that and calculate the thickness. Okay. Till that is what will be required. Okay. Now, if the pressure is exceeding to even shell and roof, then this is what we'll be doing as an additional calculation, PF, failure pressure. Okay, that you have to calculate. And then after calculating failure pressure, you'll be calculating some uplifting. Okay. You'll see whether because of pressure, the tank is getting uplifted. Okay. Now you'll see that how because of pressure that will be uplifting. So for this case, what it is considered is that if this is my tank, this is the bottom plate. So because of internal pressure, if this joint is failing, okay, then there will be uplift. Okay. It will move up. Okay. So to check that, okay, you need to use this equation E and B. What exactly is that? What you're calculating is the counterbalancing weight in addition to what we have calculated for 5.12 shall be designed so that the resistance to uplift at the bottom of the shell is greater than the following. Okay, so you have to calculate a weight, counterweight, which can be added. How much counterweight? How you'll be calculating that counterweight? Yes, calculate that uplift produced by 1.5 times the design pressure. Okay, so counterbalance weight should be calculated based on considering the uplift not only by design pressure, but 1.5 times the design pressure. And that much additional weight has to be added on the tank. Okay, so maybe on the shell or on the roof. Okay, anywhere. Second, okay, the uplift produced by 1.25 times the test pressure. Both the calculation. First, you'll be doing by design calculation, design pressure, and then by test pressure. Okay. So counterweight should be good enough. So finally, what you're making sure that the weight of the roof plus shell is becoming higher than the pressure. Does it make sense? By using a counterbalancing weight, you're again making sure that weight of the roof plus shell is becoming higher than the pressures. You are not doing any additional safety or welding some members, but just adding weight. Okay, because now the weight was lesser, it was uplifting. So the solution is add weight. Okay, make sense? So this will be done when your pressure is exceeding the last one, like it's more than the shell plus roof weight. So that is what is there in Annexure F.
For in-depth training. And to learn more about these courses, register with the link in the description.